Hi, I'm Professor Seth Chandler from the University of Houston Law Center, and this video is part of the series of videos for the course Analytic Methods for Lawyers. It's on causal inference, the reconstruction of omniscience. It's the third part in a four-part video series on causal inference. The prior videos looked at the matter from the do calculus perspective. Today, we're going to be looking at it from the potential outcomes perspective. What I want to do is to basically present this issue as being one of missing data. We know what happened when, for example, the person received treatment A for his kidney problem, but we don't know what would have happened if they'd received treatment B. That's kind of a missing data problem, and there are time-tested approaches to dealing with missing data, including several methods that are implemented in Wolfram Language. I'm going to show you how to solve this problem, or at least attempt to solve it, using missing data imputation, and then we'll use some more traditional approaches, such as matching propensity scores and stratification. If you like cartoons about causation, this is about as good as it gets. It's courtesy of the cartoon series XKCD that I highly recommend. Let's start with the fundamental problem of causal inference. The problem, well, I'm going to describe what an omniscient being would see, and since we're not omniscient, you'll then see the problem of causal inference. I have data on 100 individuals. I know their features X1, X2, and X3, and I know exactly how things would come out if they did not receive treatment, that's YC, and I know how things would come out if they did receive treatment, YT. Now, they can't both receive treatment and not receive treatment. And so the issue is I'm only going to have data for each of them. I might have a YC fit value, I might have a YT value, but I'm not going to have both. And the question is sort of, can I impute, can I figure out clever ways of figuring out what would have happened in these alternative futures? So let's work through this. And I'm actually going to move through the code fairly swiftly so that we can get to the point. Here's our data set. This is what the omniscient being sees or created. We have the values x1, x2, x3 for every person. And we have the value YC, which is the outcome when they were in the control group and didn't receive treatment, and the outcome YT, which is the outcome when they did receive treatment. And we're supposed to know both of these for each person. Okay, so that's what we have, and if we look at the average treatment effect, we can look at the mean value of the outcome for YC when you did not receive treatment and were in the control group, and the mean outcome for YT when you did. And you can see, let's just evaluate that, and it changes each time because of randomness, but it's 13.9 for the people who were in the control group, 16.9 for people who were in the treatment group. So people in the treatment group, the omniscient being knows, did better. Treatment is a good idea in this scenario. Is it statistically significant difference? Yes, it is. Okay, we could also look at a conditional average treatment effect. And let me get rid of some of these outputs because they're going to be confusing you. We can look at people whose X2 value is greater than 11 and look at whether treatment worked for them, and it turns out that it did. Okay, so what I now want to do is actually skip down here to what we see. This is what non-omniscient beings see, and what they see is that, hang on one second here, we do need to evaluate a little code that I don't want to bother you with. Okay. We see whether or not they got treatment and what their outcome was in that case. We don't see, for example, for this person, what would have happened if they did receive treatment, what their Y value would be. This is the real world, and we just see what their outcome was for this person when they received treatment, for this person when they received treatment, for this person when they didn't. And now, what would we actually see if we compared if we looked at the
average treatment effect, we would see that it was negative, that treatment was a bad idea, that it went down from 17.02 in this example to 13.8. And this is basically an illusion because it's not the treatment that's causing these people to have lower values. It's the x1, x2, and x3 values that are contributing to y and also correlated with treatment. These are confounders, as it were, and therefore, in some sense, the coefficient in front of treatment is not accurate. Okay, so how do we restore omniscience? Well, one way to restore omniscience would be, and this would be a lovely way, would be to do a randomized controlled trial. If you have enough people and you give some of them treatment and you don't give others of them treatment, in a large enough group, the characteristics of the people receiving treatment and the characteristics of the people not receiving treatment should be the same. That is, they can't pick. The person can't walk in and say, I want treatment, I don't want treatment. Rather, they're randomly assigned. And so a randomized controlled trial is a great way of determining causation. The problem with randomized controlled trials is that they're expensive. You've got to plan them, you've got to monitor people, and in some instances a randomized controlled trial might be unethical. Imagine, for example, you have you want to see whether vitamin D prevents COVID, and so some people are given vitamin D and other people are given a placebo, and then we stick them all in a room full of people sneezing and coughing with COVID and sees what happens. That is not a very nice experiment. So what we have to be able to do is to figure out how to basically restore omniscience without the benefit of a randomized controlled trial. Okay, so I'm going to talk about this as a problem of missing value imputation. That is, in one way, what we see, actually I guess I'm going to go down here. This is what we see in some sense. Here's this person. Okay, we know their x1 and x2 and x3 values. We know they didn't get treatment, and we know what their outcome was. This person, we know their x1, x2, and x3. We know what happened when they did get treatment, but we don't know what happened if they hadn't gotten treatment. And so all of these items are missing. But computer science has a lot to say about how to impute missing data. And maybe if those methods are good, we can kind of fill in the values for yc here and fill in the values for yt here, and then look at the means if this method actually works. So we're going to use a method of unsupervised machine learning called learned distribution. And let's do that. What we're doing basically is we are learning the distribution of the data. What we can then do is use a Wolfram Language function called synthesize missing values. Here's the distribution, here's the data, and it basically hunts for missing data and tries to figure out how to fill it in. So let's run this. Okay, and if all goes well, let's see what happens. Again, I apologize for these outputs. They're left over from some earlier work. And what we see is that we have actually kind of succeeded. That is, now it looks as if the treatment group is doing somewhat better than the control group. We haven't fully fixed it because the difference originally was 3 and now it's just 0.7, but at least we've gotten things in the right direction, and if we look to see whether it's statistically significant, basically it is. So in some sense, one line of Wolfram code appears to have solved the problem. One line of Wolfram code has solved the fundamental problem of causal inference. That's a bit of an overstatement. And in fact, I wouldn't say I rigged it, but I certainly helped it along. What we can do is we can use different random seeds in this non-deterministic missing data synthesis. And what we're going to see is that the results that I get depend on just random factors. Sometimes, actually I just had a good run. Sometimes the treatment is better. Actually, in all of these examples, it is. Other times, I can tell you quite honestly, we do not get as good results. And indeed, it depends on weird things like the method that I use to learn the distribution. Here I'm using a method called kernel density estimation. We're going to hope that that is not an important error message. And now we'll synthesize the missing values, learning this new learned distribution, and we'll see what happens. And what we see is that now it's still the case that the control group does better than the treatment group. And so much as I would be delighted if synthesizing missing values could just solve the fundamental problem of causal inference, in truth, it's not really powerful enough, not a dedicated enough method to do so. But it does kind of point us conceptually in the right direction, which is to say that in some sense our problem is that we have missing data. Let's try another sort of very Wolfram-y way of trying to solve the fundamental problem of causal inference, and that's to use anomaly detection. The insight behind anomaly detection is to think about why is it that we're getting wrong results when we just do sort of a raw comparison of how the control group did and how the treatment group did. And the answer is those confounders, the features, which in this area tend to be called covariates, but it's the same thing. The covariates of the untreated group look a lot different from the covariates of the treated. And therefore, when we just compare the control group to the treatment group, we're not getting a good answer. So what we would like to do is to make the distribution of covariates among the treated and untreated about the same. It's the same idea as using a randomized controlled trial. In a randomized controlled trial, if it's really random, you'd expect the fraction of rich people in the untreated group to be the same as the fraction of rich people in the treated group, and the fraction of men in the treated group to be the same as the fraction of men in the untreated group, etc. And so if what we can do is just eliminate sort of people who are outliers, we can make the two groups more similar and maybe then do a comparison. So let's actually see how we do this. We're going to do anomaly detection on the data, and we're going to create something called an anomaly detector function. All right, and now what we're going to do is we are going to basically get rid of people. We're only going to keep people if they're in the treatment group or they're in the non-treatment group, the control group, but then only if they don't have anomalous covariates in terms of the treated group. So we'll keep the treated people, and we're going to start to throw people out in the control group when those people don't look like anybody in the treated group. And that's what this code is attempting to do. You'll notice instead of 100 people, we now have 60, but we could now see, now is the outcome among the treated different than the outcome among the untreated? I'm going to skip that piece of code and that piece of code, and we'll go right down to here, and we'll see that actually this worked decently. That now of the 60 people we've got left, the people in the treatment group did better, 13.8 to 12.2. We still don't have quite the right number. This should be 3 bigger than this, but we're doing better. But once again, I have to confess, I kind of rigged this trial to use various options to anomaly detection to kind of make it work. My purpose, again, is to get you thinking about why what I'm going to show you, which are the accepted methods, work. And it's because essentially they're either throwing out people who are anomalous or trying to kind of fill in data. The first time tested method I want to discuss in the potential outcomes field is called matching. And there are hundreds and hundreds of articles that use matching, and you can very quickly get bogged down in all sorts of technical issues about the distance metric and the matching protocol. And while some people might find them very interesting, I think they're a little bit of a distraction at first. Let me explain how matching works and how it's different a little bit from anomaly detection. In anomaly detection, what we just did was to throw out some members of the untreated control group, but we didn't specify then which remaining members of the untreated control group matched members of the treatment group. We just said that sort of statistically the two groups were similar to each other. Matching goes a little farther, and it kind of emulates cloning, and the sort of cloning I talked about in connection with a randomized controlled trial. The idea is to construct identical twins, one of whom receives no treatment and one of whom receives treatment. And so since the twins are identical, we've kind of gotten back to omniscience. I know what the same person's score would be for treatment and non-treatment. And so we can then look at the average treatment effect. So how do we do matching? And there are a lot of methods that use matching. A lot of them rely on something called the Mahalanobis distance, which is a very interesting distance metric. But before I get there, let me do something that's simpler, which is just looking at something called the Euclidean distance, okay? So you've seen the Euclidean distance before. You take basically the sum of the squares and take the square root of the sum of the squares. So if one point is 348 and another point is 195, then the differences between the coordinates are 2, -5, and 3. And then we just square those, so we get 4, 25, and 9. And then we add them up, and we get 38. And then we take the square root of that as the square root of 38. And so the Euclidean distance between 348 and 195 is the square root of 38. So now what I'm going to do is I'm going to generate one of those nearest functions that finds the person in the control group that is nearest to some x1, x2, x3 value. So you see here I'm selecting people in the control group, and now I'm creating a nearest function that for any value of x1 and x2 and x3, it will find the nearest partner in the control group. All right, so we can evaluate that code. We get a nearest function, and so supposing I have a person for whom their features are 10, 23, and -7, and maybe they have some other values, but I don't care about them. I want to know who's nearest to them. And it turns out to be a person with 9.26 as value x1 and 22.4 as value x2 and -4.6 as value x3, and then some other stuff. And now we want to start running a dating service. We want to use the nearest function to match each person in the treatment group with the most similar member of the untreated control group. Now, it's not a great date because the untreated control member is totally passive. They have to accept the attentions of whatever members of the treatment group happen to be close to them, but we won't get into dating ethics here. What I want to do is I'm going to make a little graph that's going to show you how the people match up. Oops. And I can kind of try to visualize it for you. The blue people are in the control group. They're potential partners. The treated people are the tan people. And I've tried to draw arrows showing how each person in the treatment group ends up dating someone in the control group. And that's a little hard to follow because it's three-dimensional. So I tried this. Here's sort of a two-dimensional representation where you look at each person in the tan treatment group dates someone in the control group. And what you can see, by the way, is we've got kind of some polygamy going on here, or there are some people who are very attractive and then a lot of the control group is left out. What this means is this puts a huge amount of pressure on the values of the people who get dated a lot. If one of these people, let's suppose this person, happens to have an anomalous Y value, it just happened that they had a very high good outcome, that's going to throw off our data because there are just so many people attached to it. But at least these people are pretty similar to those people. And so this is the idea of matching, is that you want to have only people that are similar to each other in the control and treatment group. So what we can do now is we can see that it worked. And yeah, it did. The treatment is now about 2.2 better than the control group, which is close to the truth, which we know from our earlier omniscience, is about 3. Well, I just gave you the idea of matching, but I also showed you a potential issue with matching, which is just having some people in the control group who are just too popular, and therefore they have an undue effect. So there are all sorts of ways of dealing with that. I'm not going to go through the code of how you actually do it. I'm going to sort of show you the picture where maybe if you can only be dated by 2 people at most. And so if your person who's nearest you has already been taken up by 2 people, you got to move on to your second choice. And when you do that, actually, you can see that we do still get an effect in the right direction, but it's not quite as good. And so my point here is simply to point out that there are all sorts of complications to matching. I just dealt with how many matches do you get. I'm now going to deal with another complication, which is the distance metric. Remember, I used the nice Euclidean distance up here when I computed my nearest function all the way up here. But that's potentially a problem. Supposing x1 is someone's height, but it's measured in miles. And so, one person is 1/1000th of a mile tall, and another person is 1/1002nd mile tall. Not much difference between them. Whereas their weight is measured in micrograms, or I guess we should make it milligrams. And so one person weighs 70,000 milligrams, and another person weighs 60,000 milligrams. So if you don't know the units, the weight figure is going to totally dominate the height figure. And so you have to come up with some way of normalizing the units so that they're scaled about the same. Moreover, sometimes the information in the columns could be kind of duplicative or correlated with each other. And the solution to this is to use something called the Mahalanobis distance, which basically tries to put everything on the same scale and tries to deal intelligently with the problem of correlated data. I am going to skip the gory details of how you actually do a Mahalanobis transform in Wolfram language, and again get to the point here, which is that all we're going to do here, the only thing that's different, is we're going to compute the nearest function using a Mahalanobis distance function measure rather than the Euclidean distance we did before. When you do that, you get different matches. You still can have the problem of multiple matches, but they're different people. You could also you could do the same thing where you prevented someone from being dated by someone, or being dated by more than 2 or 3 people. In any event, the bottom line is that when you do this, you get a result in the right direction, which is that the treated group has a 13.8 and the untreated group has a 12.7. Again, I think the key point is to understand that there's a whole complicated technology associated with how you do matching. The distance metric and the protocol for dealing with multiple matches are important. And so, and the results may change depending on how you do it. So if you see someone doing a matching study, you do need to investigate how it was that they did the match. Okay, so why do we have to go through Mahalanobis matching? And At bottom, it's because the variables are scaled differently. And if we're going to use a distance metric, we have to address that point. There's another method, though, which again, I guess 93,000 academic papers use this. It's called a propensity score. Here's the fundamental idea. The fundamental idea is that if two people would be equally likely to receive treatment, but as it happens, one did and one would not, those two would be good people to pair up in sort of a pseudo-randomized controlled trial. You want to kind of match people based on their propensity for treatment. And by the way, you should know that you're going to see, like everything else in causal inference, everything has multiple names. Sometimes this method is called inverse propensity weighting, or it's called inverse probability of treatment weighting, IPTW. In my opinion, that's the best name because that's actually what's going on. It depends on the inverse probability of treatment and weighting people that way. Okay, so here's how we're going to do it. The first thing we're going to do is to figure out what determined whether people got treated or not. And this is just a logit model fit, a logistic regression, where we're running x1 and x2 and x3, but not on the outcome, not on what happened, but on whether they got treated or not. So we can do that. That's a fairly simple thing to do. And we can look at the parameter table and see if our model's any good. And yeah, it doesn't look like x2 is surviving a p-value test. In fact, none of them are really surviving a p-value test. Maybe the variables are correlated with each other, but we end up with a model that has a respectable Krag-Euler pseudo-R squared, and so at least we have some model of propensity. Moreover, we better make sure that we have diverse levels of propensity, and in fact we do if we look at a histogram of the predicted propensity levels of being treated. We can see that it spans the zone from 0 to 1. So that's good. Footnote, I've seen studies which use propensity weighting where that wasn't true, and basically no one noticed that, and so they make no sense. In any event, what we can now do is augment our data set and include the propensity value for each person. So let's run that. And right, it didn't round here for reasons I'm not sure about, but I'm not going to stop the video. It's the same number. It just didn't round for us. Okay. Now let's do the weightings. Okay. If the person is in the control group, we're going to weight their observation by 1 divided by the propensity. So if their propensity was low, we're going to weight them heavily. If, on the other hand, the person is in the treatment group and their propensity is high, then we're going to weight them heavily. And so here's what we're going to get. For each person, we're going to get their weights. Okay. Now, what we're going to do is we're going to compare the weighted average of the people who received treatment and the people who didn't receive treatment. Okay? And so when we do that, we find that the people who got treatment did about 2.6 better than the people who didn't receive treatment. So this is a pretty good response. And so even though there is an entire industry devoted to telling you that propensity scores are not a good way to do causal inference and you should do certain variants of matching instead, and even though I think actually that criticism is correct, in this particular instance, propensity score matching did pretty well, and I suspect in general it does fairly well, and the technology isn't that hard of doing. We've known how to do logistic regression for a long time, and so this may explain why we've got 93,000 papers that use propensity score. Here's something you might have been thinking about. you use logistic regression to determine propensity. But we learned in this course that there are all sorts of ways of coming up with a model for the probability of treatment. We could use a neural network or a random forest or all sorts of other supervised machine learning algorithms. Or maybe we could use logistic regression but have different basis functions. And so how fragile is propensity scoring to the choice of the propensity determination method? That's what all this code is about, and it turns out it is actually somewhat fragile. And in fact, when I did it this way, you can see when I used random forest, it got the result wrong, backwards. And so this is a problem. Using the inverse of propensity scores to weight the data works reasonably well, but it's not a panacea. The other thing that sometimes people do is to use propensity scores to do matching. That is, you find people whose propensity for treatment is roughly equal in the you do the same thing. You look at people who haven't been treated, you compute their propensity score, and you find people in the treatment group whose propensity score is similar. You do the matching. Again, you could add the bell and whistle of only permitting a certain number of people to date you. And actually here, this worked out pretty well. What I've set forth here, this is sort of the lead critic of propensity score matching, a professor named Gary King at Harvard. You can watch some of his videos where he spends a long time telling you how terrible propensity score matching is. One final method from the potential outcome school of causal inference. It's called stratification or clustering. Here's the idea. It's the same concept as matching, really. Let's get people who are similar to each other in terms of their covariance. So let's perform some clustering that groups people together. The Wolfram Language command to do this is cluster classify. So we're going to build a classifier that can take a person's x1, x2, and x3 values and assign them to a cluster. Okay, that person goes to cluster 1. This person goes to cluster 2. That person goes to cluster 2. I don't know. I'm having trouble getting someone to cluster 3, but trust me, there is somebody. All right, and now let's take everybody in our data set and assign them to a cluster. All right, there they are. They're in their little clusters. And now, by the way, if you want to see what the clusters look like, we can see here are the brown people, the purple people, and the green people. So now what we can do is, since these people are kind of alike in their covariance, and these people are kind of alike in their covariance, and these people are kind of alike in their covariance, we can get the conditional average treatment effect for each cluster. And we could just make sure we got roughly the same number of people in each cluster. We're going to compute the conditional average treatment effect within each cluster. We do that, and then we can basically weight the conditional average treatment effect by the fraction of people that are in each cluster. And at the end of the day, we end up with an average treatment effect. It works. Again, it's a little arbitrary. Why did I pick 3 clusters? I could have picked 4 or 2, and the results would actually have been different. But conceptually, this is one of the methods. And again, this is why you have to ask questions when you see people doing causal inference studies or any other analytic method study. A lot of these methods are very fragile, and the results that you get depend on these little picky details of how you do it. All right, so we've taken a tour, a survey of some of the methods used in potential outcomes. The question that you might consider is, given how fragile this all is, should you use it? And I have to say, I am not a big fan of potential outcomes. It's one of the reasons I didn't stress it. It's a little simpler, and you don't have all the forbidden set stuff that can get complicated. But at the end of the day, probably you need to know both methods, because you're going to see both methods if you work in this field or do litigation in this field. But if it were my pick, I would tend to go for the do calculus of Judea-Pearl. Okay, so what's left? We've got one more video on causal inference. It's going to look at some sort of special methods in causal inference, two that are used in econometrics, one of which I'm very fond of. One is difference in differences, and the other, which I really like, is called regression discontinuity. We'll see those in our next video. Thanks.